Okay, Assalamu alaikum and Bismillahir Rahmanir Rahim. So, in today's lecture, this is going to be our third lecture and our second one online. So this is the layout for today's lecture. Here we basically see like what did we discuss in our last lecture. So, in our last lecture, we talked about digital systems and then computer systems. We talked about information representations. We spent quite some time on number systems, and then I'm not sure whether we did arithmetic operations or not. We are going to do arithmetic operations in this particular lecture. We did base conversion. We learned how to convert from decimal to binary, from binary to decimal, or from decimal to any other base in general. And then we also learned how to convert from binary to octal and hexadecimal. And we discussed the special relationship between these number systems. We started to talk about different decimal codes. We learned the difference between conversion and coding. We gave an example of that as well. Here we'll complete our discussion of those codes, and then we'll talk about binary arithmetic. Binary arithmetic is very important. We should know how to add binary numbers or how binary numbers are added, and then how they are subtracted, multiplied, and similarly, we should have an idea about their division as well. But in this particular lecture, I guess we'll only discuss their addition, subtraction, and uh, multiplication. Then we'll talk about alphanumeric codes. So alphanumeric codes, again, they are codes to represent or to, this is basically a notation for alphanumeric data. So all these characters on your keyboard, the printable and non-printable characters, so they are represented in using some particular codes. So one of them is ASCII, the other one is Unicode. We'll talk about both these codes. And finally, then this overview does not show it, but later on, this is basically a continuation from the previous lecture. This is what we couldn't complete in our last lecture. So that is, we'll complete that discussion, and then we'll talk about logic gates and binary variables and a little bit about Boolean algebra and the basic operations. We did that discussion in our first lab session as well. So we'll just repeat that. It was meant to take place in some theory lecture, but we did it because the lab approached first and we had to do something in the lab. So let's start. Here I have deliberately put this slide on course learning outcomes. You should always go through it and you should uh, recall what are the objectives for this course or what are the learning outcomes that you want to achieve. So this is why you're studying this course and this is what you want to achieve. Okay, so we are still working on the first learning outcome. We are still working for that. Okay, so first we'll start with binary arithmetic. Okay, so binary arithmetic, we will first learn how single individual bits are added and how that addition uh, is done when there is a carry from a previous addition. So we look at these possibilities. Then we'll extend this single bit addition to multiple bit addition. So we'll just go through it so that you have a clear idea about it. Now you are familiar with decimal addition, and that is very easy. You've learned it in your very elementary classes, and we are going to apply the same rules, but the only difference is the number system. It's going to be base 2 or binary number system, and that is going to change things a little bit. Okay, so if you pay attention and you're cautious, careful, it won't be a problem. Then we are going to look at single bit subtraction. Again, subtraction in decimal is very easy. You can do subtraction in decimal, you can handle the borrow and all that. But when it comes to binary, then things may get a little tricky. They're not that tricky, but since we are not used to binary, they look a little tricky. And then we will do extend that single bit subtraction to multiple bit subtraction. And that is how it actually happens. Like in digital systems, we we, we basically implement an operation for a single bit, and then when we do that, we create a block, a digital logic block that can carry out single bit operation. And when we want to carry out multiple bit operations, so we employ multiple blocks, multiples of those blocks, we employ them and we put them in a cascade so that they can do multiple bit uh, operation, whether it is addition, whether it is subtraction, whether it is multiplication or any other thing. We'll also look at multiplication, again single bit and multi-bit, and then we will look at BCD addition, binary coded decimal addition. So if we want to add binary coded decimals directly. Now BCD addition is different, okay? So it is just like decimal addition, but we are doing it in binary. So we'll be adding decimal digits, and those decimal digits would be coded in binary. So we want to be able to add them, and we want to have the correct answer, and the correct answer that we expect, it should not be in binary, it should be in decimal. Decimal that is coded in binary, okay, or binary coded decimal. So we'll look at this as well. So let's start. First of all, single bit addition. Now single bit addition again, whenever you're doing addition, if you're adding two numbers, so if those numbers have some digits, now you don't just add those two digits. There is a possibility that you may have a carry from a previous addition, okay? Or if you add two digits or two bits, so when you add them, the sum may not be a single digit sum, okay? So there may be a carry out. So you will learn these terms, carry in and carry out. Okay, carry in and carry out. So carry in is basically a carry from a previous addition, and carry out is a carry from the current addition. Okay, the digits that you are currently adding. So whenever you're doing addition, you should always keep in mind a carry in from a previous addition. Okay, that is, if you're going to design an adder, the adder must take into account a carry in from a previous addition. Okay, so later on, when we are actually designing these circuits to do addition, so we differentiate between the two. We have a circuit called a half adder. So a half adder does not take into consideration a previous carry, and then we have the full adder. The full adder takes into account the previous carry from the previous addition. Okay, so here are the symbols that we are going to use. We will have two single bit binary numbers, x and y, and we will have a carry in. We represent it by z, okay, and the output that we are going to get is sum and carry. So we are going to get the sum as well as the carry, okay. So we are going to get two outputs, not just one output. Okay, so they are both single bit outputs. They are both single bit outputs. And we are going to look at two different scenarios. One where there is the carry in from the previous addition is 0. Second one where the carry in from the previous addition is 1. So let's look at these two possibilities. Now, in these two cases, the carry in from the previous addition is 0. Okay, and these are these two numbers, x and y. These are single bit numbers. So these are their all possible combinations, 0, 0, 0, 1, 1, 0, 1, 1. Okay, so we will look at each one of them. Let me get the pen. Okay, okay, so 0 plus 0, 0 plus 0, 0 plus 0 is 0. Okay? But we are not just going to add 0 plus 0, we are going to add the previous carry as well. So 0 plus 0 plus 0, these are three zeros. So the sum is 0 and there is no carry out. So the carry is also 0. 0 plus 0 plus 1. Okay, so this is 1. The sum is 1 and there is no carry out. There is no carry out. The sum is a single digit sum, so you have 0 carry out. Similarly, 0 plus 1 plus 0. Here also we have the sum equal to 1 and there is no carry out. Okay. Here we have both x and y as 1. The previous carry is 0. Now if you add 1 and 1, you get 2. 2 in binary. So the sum is 2 in decimal. And in binary, we can represent this sum as 1, 0. Okay, 1, 0. So here 0 would be taken as the sum and 1 would be the carry out to the next position. 1 would be the carry out to the next position. So this is how we write. Although you can say like 1 0 is the sum, why call this part of the sum as carry? But here like sum y, x and z, they are all single bit. They are all single bit. And when you add 1 plus 1 you get 2, so 2 cannot be represented in a single bit, so there would be a carry out, there would be overflow. Okay, this is what we call overflow, so we can call it as overflow. Now the sum cannot be stored in a single bit, so it will overflow. We call it, you can call it overflow or the carry. So this is a carry out. Okay, understand? Now let's look at the second uh, case where we have a carry in of 1, like there is carry from a previous addition. So if we are adding multiple bits, so we can have carry from a previous addition. So I guess like this is clear. Like for example, take an equivalent example in decimal. So say we have previous carry 0, and then say for example x is 9 and y is 1, say for example. So 9 plus 1 is 10. Okay, and we know in decimal that this is how we write 10. Okay, but if the sum were to be represented in a single digit, then this is your sum and 1 is your carry. Okay, so this would be interpreted as the carry. Okay, so in decimal there are more possibilities as well, like in which you can get 10. So you can have 5 plus 5 or 6 plus 4 and all those combinations. And in each case, you will have 0 as the sum and 1 as the carry. Okay? So whether we should call 10 as the sum or we should call 0 as the sum and 1 as the carry. Now this is important in computing or in digital design. Why? Because you have a finite number of bits to represent the sum. So here the previous carry, the number x, the number y, they are all single bit. The sum will also be single bit. Okay. If the sum cannot, the sum of these three, the sum that you calculate, if it cannot fit into this single bit s variable, then whatever comes out of it, that will be called the carry. Okay. So इसमें कंफ्यूज नहीं होना कि ये 1 0 तो सम है, तो इसमें हम इसको कैरी क्यों कहते हैं और इसको सम क्यों कहते हैं. ठीक है, कैरी और सम के नाम हमने इसलिए दिए हुए हैं कि ये डिजिटल सिस्टम्स हैं. बाकी सिस्टम में भी ऐसे ही होता है, बट डिजिटल सिस्टम्स में वी आर particularly careful about it because we have a very limited number of bits. So usually whatever is the size in terms of bits of the input variables, वही output variable का भी usually size होता है, especially for operations like addition, subtraction, even multiplication, division के लिए भी तो वही size होता है. ठीक है. For example, the processors or computers that we are using, for example, like the laptop that I am using, it has a 64-bit processor. Okay, 64-bit processor. Now what does that mean? That means it can add two 64-bit numbers, say in a single cycle. In a single cycle, it can add two 64-bit numbers. The sum has to be 64-bit as well, क्योंकि ये जो sum calculate होगा वो इसी processor के किसी register में store होगा. ठीक है. Now there's another term, register. ठीक है. So what is a register? A register is basically a storage device. A register is basically a storage device. ठीक है, or a memory device. So it is a sequential logic circuit. A register is a sequential logic circuit. Why? Because it has memory. It can be used to store something. Now register has multiple cells. ठीक है? Another term, a cell stores a single bit. A cell is used to store a single bit. So a 64-bit register will have 64 cells. Okay. So in general, n-bit register will have n cells. N-bit register will have n cells. Okay. So this computer is 64-bit computer. That means internally it has a 64 bits, it has 64-bit registers to store data, and it has a 64-bit ALU, arithmetic and logic unit. It has a 64-bit ALU, arithmetic and logic unit. That means it can add 64-bit numbers, it can subtract 64-bit numbers, it can AND or invert 64-bit numbers, and the result is also going to be 64-bit. Now, if the result somehow exceeds 64 bits, then we have a carry bit as well. So inside the CPU, we also have the carry bit. Okay, so if the addition, the sum of these two 64-bit numbers exceeds 64 bits, it cannot be represented in 64 bits or stored in 64 bits. So there is a carry bit. So the carry bit will be set, it will turn into 1. That will mean कि ये जो sum है it has overflown, ये 64 bits में नहीं आ सकता, तो ये overflow कर गया, ठीक है. So in digital systems we are very particular about sum and carry कि ये sum है और ये carry है. तो 1 0 is not the sum, 0 is the sum and 1 is the carry. Why is 0 the sum? Because 0 goes into the sum bit, 0 goes into the sum bit, and the sum bit is just one bit, so it cannot store two bits. So this second bit, that is the carry out of here, it will go into the carry bit. ठीक है. So in any case, result को store करने के लिए we have two bits, one we call the carry bit, the other we call the sum bit. ठीक है. अच्छा, so I hope this is clear. So we introduced the concept of cell. ठीक है. Cell is just a name. It is basically any digital circuit that is used to store a single bit. A register has multiple cells. Okay, so if we have 8 cells, we will have a register, 8-bit register. Register is also a sequential logic device. Why is it a sequential logic device? Because it has memory, it stores some value. Okay, or state, it has a state that it stores. We can inside this, like we can have any we can have a register of any size, any length. Okay, so say for example, the CPU or processor inside this laptop, inside my laptop, it has a 64-bit processor. What does that mean? That means that internally the registers that this processor has, those processors, those registers are 64-bit wide. They can store 64-bit data. Okay? And it has an ALU, arithmetic and logic unit, that is 64-bit. Its size, the size of the ALU is 64-bit. What does that mean? That means that ALU can add 64-bit numbers in one cycle, can subtract 64-bit numbers, can multiply, divide 64-bit numbers, can carry out logical operations on 64-bit numbers in a single cycle. Okay? That is what it means. So this discussion came out of register. Acha. Now the second possibility, where we have a previous carry of 1, then how would the addition look like? So x or y की combinations to 0 0 0 1 1 0 1 1 and z in all cases is 1. There is a previous carry. ठीक है, तो ये हमारी एक possibility इसमें there was no previous carry. In the second one we have a previous carry. Now how would the sum and carry look like? So we have 1 0 0. So the sum is 1. There is no carry. ठीक है, this should be easy. We have 1 0 1. Okay, so now we have two ones. When you add them, the sum is like 2. In binary, it is going to be 1 0, and 1 0 cannot be stored in a single bit. So 0 would be the sum and 1 would be carry out. Okay, so this 1 should go into the carry, 1 is not going into the sum. Why? Because the carry also shows that there was an overflow, like the sum was too big to be stored in a single bit. Okay, so when it is 1, that is also an indication of an overflow. Similarly, the same for this combination. We have two ones here, so when you add them, the sum is 2. 2 in binary is 1 0, so 1 would be stored in the carry bit and 0 would go into the sum bit. Here we have three ones, 1 1 1. Okay, so the sum, if like in decimal, if you do it, is 3. 3 in binary has to be 1 1. Okay, 2 raised to power 1 plus 2 raised to power 0. So this is 3. Now here we have the sum equal to 1 and the carry equal to 1 as well. Okay, so there is an overflow as well. This is single bit addition. We can very well extend it to multi-bit addition. This is how single bits are added. Now the process, if we have 8-bit number or 16-bit number or 64-bit number, this same process has to be repeated for multiple bits. Okay, and each single bit addition may give rise to a carry. That carry has to propagate to the next higher significant bit, then it has to be added to those two bits, and so on and so forth. So this same process has to be repeated over multiple bits to multi-bit addition. Now let us extend it. For example, we have these two numbers. This is one number, this is another number. These are two different additions we are trying to do. And we have these terms. Let's call the first one as augend and the second one as addend. Okay, so this is augend, this is addend. We are doing addition. What would be the sum? Okay, or how are we going to extend it to multi-bit addition? Now let's carry out it one by one. Say for example, let's carry out this. Now here, this is the previous carry into the first bit, or the least significant bit. These are the least significant bits. So we'll assume that there is 0 previous carry into this least significant bit position. Okay. Then after the addition here, the carry may propagate into the higher bit position. Okay, that is a possibility. So let's do this addition. So first of all here, so 0 plus 0 plus 1, this is 1. The sum would be 1, and there is 0 carry. 0 as carry. There is no carry out into the next bit position. So we represent it as 0 carry. Then add these 3. Okay. So now I guess you would realize, why did we consider here the carry in? Why did we always consider here the carry in? Why? Because whenever you add 2 bits, here the carry in is assumed to be 0. So there may be a carry out. For example, if it were 1 1, okay, if it were 1 1, so there would be a carry out 1. That would be significant. Right now the carry out is 0. It is not that significant, but in any case you should always consider a previous carry. Okay, so in this case there is no previous carry. Similarly, if you add these 3, the sum is 0 and there is no carry out. So again the previous carry is 0. So this is carry from the previous addition, or carry in. This is carry from the previous addition, or carry in. We may call it as C sub in. Okay, so this is carry in. Now add these 3, 0 plus 1 plus 0. Okay, this is 1, the sum is 1, there is no carry out. Okay, there is no carry out of this addition. This addition did not produce any carry out. It produced a carry out, but that carry out is 0. When I say that it did not produce any carry out, by that I mean like the carry out was not 1. Okay, so it did produce a carry out, but that carry out was 0. Now this bit is a carry out of this addition, but a carry in for this addition. Okay, so you should know these subtleties. This same bit can have two different names. It is a carry in from a previous addition, and it is a carry out from this addition. Okay, now add these 3. Again we'll get the sum equal to 1 and the carry equal to 0, and then add these 3, we have the sum equal to 1. Okay. Okay, now let's get here. You can look at the decimal values of these numbers. So this is 8 plus 4, 12. Okay, this is 12, and this number is 16 plus 1. Okay, its weight is 16, and this is 1, this is 17. So the sum is going to be 29 in decimal. And see, this is 16 plus 8, 24 plus 4, 28 plus 1, 29. Okay. Now let's look at this addition. So again, the carry in from the previous addition, like there is no previous addition when you are adding the least significant bits. So that's why we always assume it to be 0. Add these, you will get the sum equal to 1, and there is 0 as carry out. Now add these three, 0 plus 1 plus 1. So you will get 2. That means your sum is 0 and 1 is the carry out. Okay. 1 plus 1 plus 1, that is 3. That means 3 in binary is 1, 1. So 1 is your sum, 1 is the carry out. And 1 plus 0 plus 0, this is 1. Okay. And there is no carry out. And similarly 0 plus 1 plus 1, so there is sum is 0. This is यानी ये 2 है decimal में, 2 decimal में binary में 1 0 होता है, and 1 is the carry out. Okay, so 1 is the carry out. So these two numbers are 5-bit numbers, ठीक है, and their sum has overflown. Their sum has overflown. Their sum cannot be stored in 5 bits. अच्छा ये कौन से numbers हैं decimal में? So let's practice our binary to decimal conversion. So this is 16 plus 4 20 plus 2 22. ठीक है. This is 16 plus 4 plus 2 uh, 22 plus 1 23. Their sum would be 45. Okay, 45. Is this 45? So this is 32. 32 plus this is 8, 40, 44, 41. Okay. Okay. So this is how binary addition can be extended to multiple bits. Okay. So you can take any number of bits and extend this process to those multiple bits. These are 5 bits. You can extend it to 8 bits, 32 bits, 64 bits, any number of bits. Okay. Now, single bit subtraction. Subtraction may be a little bit tricky. Okay, subtraction may be a little bit tricky. So you have to pay careful attention to it. Now, in addition, when you add two numbers, we have a carry out. In subtraction, we have a borrow. But the borrow and the carry, they work differently. Okay, so you have to pay careful attention here. You have to understand it well. So here we are going to add, we have two binary digits x and y. These are single bits. And we have a borrow in z. Okay? We get the following difference and borrow. So when we are basically adding these two subtracting y from x, we are finding out x minus y. So we can have a difference. We call it S. Again, we are not calling it D. And we can have a borrow. Like we may need to borrow something. If we are borrowing something, we represent it by 1. If we are not borrowing something, we represent it by 0. Okay, so that is a borrow from the next higher position. And here it is called borrow in, but this is basically a previous borrow. Whether there was a borrow from this current position in the previous subtraction or not. So when we look at it, we will basically understand. Okay. Acha ji. So let us look at all the possibilities. Now uh, here we assume that the borrow in is borrow in or z is 0 in the first case, and in the second one we assume that it is 1. Okay. So we are going to calculate x minus y. Okay. We want to find out x minus y. Okay, but there might have been a borrow from this position. Okay, there might have been a borrow from this position, a previous borrow from this position. So essentially we are doing this calculation, x minus y minus z. In the first case, we assume that there was no borrow. In the first case, we assume that there was no borrow. In the second one, it would be a little different. Okay, so let's see. In all these cases, z is equal to 0. So we are going to do x minus y. Okay? So 0 minus 0 is 0. And in order to subtract 0 from 0, we did not need any borrow. So borrow is 1. Borrow is 0. Okay. Now, next we want to do 0 minus 1. Okay? Now, we cannot do 0 minus 1. Why? Because 0 is small and 1 is big. So what should we do? We should borrow from the next higher position. We should borrow. In decimal, when you borrow a 10. In binary, when you borrow from the next higher position, you borrow a 2. Okay? You borrow a 2. So 2 minus 1 is 1. That is your difference. And borrow would be 1. Why? Because you borrowed. You had to borrow. So that's why borrow will be 1. Again, it works differently. Okay? The borrow works differently as compared to the the carry. Okay? The carry is automatically like calculated, and the borrow, like you have to do some kind of reasoning in your head. And here the case is simple because there is no previous borrow. There is no previous borrow. So we are outright ignoring that. That is 0. So things are very simple. Now here we are going to calculate x minus y. X is bigger than y. 1 minus 0. So the result is 1. We did not need to borrow anything in order to carry out this subtraction. Okay. And here again 1 minus 1 is 0. They are both equal. We did not need to do any borrowing in order to carry out the subtraction. Okay. So this was relatively easy. The next one is a little trickier. Okay. Okay. So you should remember this, that we are actually calculating this thing. We are actually calculating x minus y minus z. That is what we are calculating. Why are we subtracting z? It is called borrow in, but it should be borrow out. Okay? It should be called borrow out. I tend to differ here with the guy who prepared this slides, the authors basically. So it should be x minus y minus, this is what we are trying to calculate. So this is not a borrow in, this is basically a borrow out. Like, was there any borrow out from this position? So when z is equal to 1, that means when there was a subtraction in a position here, so they needed a borrow, so they borrowed 1. ठीक है, तो आपने जहन में ऐसे assume करना है कि ये borrow 1 जो हम यहाँ पे 1 assume कर रहे हैं, इसका मतलब क्या है? इसका मतलब ये है कि फॉर एग्जांपल अगर हम assume करें मल्टी बिट सब्ट्रैक्शन, तो इससे लोअर बिट पोजीशन पे जब सब्ट्रैक्शन चल रही थी तो उनको बोरो करने की जरूरत पड़ गई. ठीक है, so z is equal to 1 means के 1 was borrowed out of this position already. 1 was borrowed out of this position already. ठीक है. Now 0 minus 0 तो fine, it is fine, but since 1 was already borrowed, we have to do 0 minus 0 minus 1. ठीक है, और वो हम that we cannot do because 0 छोटा है और 1 बड़ा है, so we have to borrow from the next higher position. ठीक है, तो ये borrow bit जो है वो set हो जाएगा. It would be 1. Why? Because in order to find out this thing, we need to borrow. क्योंकि z 1 है, although y 0 है और x 0 है, x minus y कैलकुलेट करने के लिए तो हमें कोई ज़रूरत नहीं है, लेकिन z is 1. Previous borrow यहाँ से हो चुका है एक. So we need to borrow from the next higher position. ठीक है, so वो borrow हम specify करते हैं by 1 कि ये borrow हमें चाहिए, और जब हम borrow करते हैं तो we actually borrow 2. ठीक है, so then we say ये जब borrow कर लिया तो it is 2 minus 0 minus 1 which is 1. So difference आपका 1 होगा and borrow would be 1. ठीक है, so it is important that you understand it. Next, we want to calculate 0 minus 1. Again x छोटा है, y बड़ा है, और ना सिर्फ ये बल्कि यहाँ पे there is a previous borrow as well. ठीक है, so in this case we need to do something like this: 0 minus 1 minus 1, which is 0 minus 2. ठीक है, which is 0 minus 2 in this particular case. So this cannot happen. Why? Because 0 is small, 2 is big. So what should we do? We should borrow. We should borrow from the next higher position. ठीक है, अब आप कहेंगे कि next higher position पे तो कुछ है ही नहीं. बिल्कुल नहीं है, आपकी बात ठीक है. That is why we specify कि in order to carry out this subtraction we had to borrow. So ये borrow bit हम set कर देते हैं. ठीक है, तो borrow bit जब set हो जाएगा, जो next subtraction होगी तो वो इस उसके लिए फिर ये z1 होगा. ठीक है, तो वो इसका फिर ख्याल रखेगा, ठीक है। अच्छा, जब हम when we borrow from this position we borrow 2, ठीक है, तो 2 minus 2 is 0, so the difference is 0 and we had to borrow, so that's why the borrow bit is set, ठीक है, that's why the borrow bit is set. Now let us look at this particular condition here. It is x is 1, y is 0, but there is a previous carry, ठीक है, तो we have to do like 1 minus 0 minus 1, so this is good enough, we can do the subtraction without having to borrow, ठीक है, so that's why borrow bit is 0 and the difference is also 0. And in the last case we have both x and y equal to 1, but there is a previous borrow, so what we are trying to do is we are trying to do 1 minus 2, which can be done. So we need a borrow from the previous position. We need a borrow from the previous position. So that borrow would be added to 1. So it will become 3. 3 minus 2 is 1. Okay? So here the difference would be 1, and we had to borrow in order to calculate this difference. So that's why we have 1 1. We have it equal to 1 1. Okay? So I hope you understand that. Now we'll repeat this in the next example when we extend it to multiple bits. Okay? Acha, now we have say this is our x, now it is a 5-bit number, and this is our y, this is also 5-bit number. We call this one as the minuend and this one as a subtrahend. So subtrahend is subtracted from the minuend. And the previous borrows for the least significant bit position, we assume them to be equal to 0. Okay, so that is always the assumption. Like we assume that when we are adding these two numbers, there was no borrow from this position. Now these borrows will be calculated later on, but there was no borrow from this position. So let's do it. So 0 minus 0, and there was no previous borrow, minus 0. So the difference would be 0, and we did not need to borrow anything. We did not need to borrow anything to do that. 1 minus 1, okay, and there was no previous borrow. 1 minus 1 minus 0. So the difference would be 0, and we did not need to borrow anything for it. Okay. 1 minus 0 minus 0. Okay, the difference is 1, and we did not need to borrow anything for it. 0 minus 0 minus 0. So difference is 0, and we did not need to borrow anything. Sorry. And again 1 minus 1 minus 0. So the difference is 0, and we did not need to borrow anything for this. Okay? Acha. So this was simple. Let us verify in decimal. These are the same numbers, I guess. Yes, this is 16 plus 4, 20, 22. So this is 22 in decimal. And this one is 16 plus 2, 20. Oh, sorry. This is 16 plus 4, 20, 22. Okay. And this is 16 plus 2, 18. Sorry, 16 plus 2, 18. So 22 minus 18 is 4. And this is also 4. Okay, 1 0 0 0 0 0 0 0 1 0 0. This is also 4. Okay, now let's look at these two numbers. These are a little trickier. Now, what are we going to do? What are we trying to do here? We are trying to subtract 1 from 0. 0 minus 1 minus 0. Okay, so this is, assume it as x, this is y, and this is z. So 0 minus 1 minus 0. We cannot do that because 0 is smaller than 1. So what should we do? We should borrow from this position. Okay? We should borrow from this position. And when you borrow, we need to specify that we had borrowed from this position. Okay, by writing it a 1 here. Okay? So we need to borrow from this position. When you borrow from this position, you borrow a 2. So 2 minus 1 is 1. 2 minus 1 minus 2 minus 1 minus 0 is a 1, and we had to borrow from this position. ठीक है? Okay. Next is we want to do this subtraction. 1 minus 1. This would be fine, but there is another one. Z. We had borrowed from this position. Okay? So we are trying to do here 1 minus 1 minus 1, which is 1 minus 2. We cannot do that. Okay? We need a borrow. Which is we need a borrow. So we have to borrow from this position. When we borrow from this position, we borrow a 2. So this 2 will be added to 1. So it will become 2 plus 1, 3. 3 minus 2 is 1. Okay? 3 minus 2 is 1. Okay. So next, we want to subtract 0 from 1. We want to calculate 1 minus 0. We can do that. No problem with that. There has been a previous borrow. That can also be taken care of. So we are going to subtract from 1, we are going to subtract 0 and the previous borrow. Okay. So this is going to be 1 minus 0 minus 1, which is 0. And in order to find this difference, we did not need any borrow. So there was 0 borrow. Similarly, this is also easy, 0 minus 0 minus 0. And in order to find out this difference, we did not need any borrow. And similarly, 1 minus 1 minus 0. So it is 0. And in order to find this difference, calculate this difference, we did not need any borrow. So this is how it would work. Now we can verify it in decimal. This is 16 plus 4 plus 1, the same number, 22. And this is 20, 21, no, 19. This is 19. This was 18. This was 18. And here just this one bit is flipped. So this is 19. So 22 minus 19 is 3. Okay. And this is also 3. So it works. Okay. This is how multi-bit subtraction works. And binary multiplication, again, it is very easy. Maybe multiplication is the easiest of all. So how does single bit multiplication work? So if you multiply 0 with 0, it's 0, 1, 0, 0, 0, 1, 0, 1, 1, 1. Okay? Now, if you remember something, we talked about the AND gate. Okay? And what is the AND gate or AND operation? So AND operation is an operation which will give you a 1 only if both inputs are 1s. And if either of the inputs is a 0, okay, either of the inputs is a 0, so it will give you a 0. It will give you a 0. So just for this one case, just for this single case, you'll get a 1. For all the other cases, you'll get a 0. That is what an AND operation is. Okay? For all these operations, you'll get a 0. Now, if you look, the binary multiplication is just like that. Okay? If any of the multiplicand or multiplier is 0, so the output is 0. And if you multiply anything with 0, you get a 0. You only get a 1 in the case of binary multiplication when both the multiplier and multiplicand, they are 1s. Okay? So single bit multiplier can be implemented using an AND gate. A single bit multiplier can be implemented using an AND gate. Okay? So the AND gate is a very useful gate. Okay? I hope now you know, like it can multiply two single bits. Now how to extend multiplication to multiple digits? Now in order to extend multiplication to multiple digits, just like you do it in decimal. For example, if you have these two decimal numbers, 223 and say 11 or 12, let us make it a little complicated. So 12. So what do? You first multiply this multiplicand with the first digit of the multiplier. 2 3s are 6 and 2 2s are 4. Okay. So this is the ones digit that you multiplied it with. Now you're multiplying it with the tens digit. That's why you leave the space for one digit, because Here you are calculating the product of this thing with the tens digit. So 1 threes are 3 tens. These are basically 3 tens. 1 twos are 200s. Okay, so this is one partial product. This is not the full product, but this is a product nevertheless. So this is one partial product. This is another partial product. And then you add these partial products. So it is 6, 7, and 2. Okay, so 276. This is what you do in decimal. You know this. Now we have to repeat the same thing in binary. Okay? Now in binary it is a little easier. Why is it easier? So see if this is the multiplicand and this is the multiplier. So if you multiply the multiplicand with a certain bit of the multiplier, that is 1, so all you need to do is write down the multiplicand. Okay, so 1 ones are 1, 1 ones are 1, 1 zeros are 0, 1 ones are 1. That's it. The next bit in the multiplier is 0, so you write 4 zeros and you shift it to the left. Okay, you shift it one position to the left and you just write 4 zeros. Next bit is 1, so you just shift it again to the left one bit position and rewrite the multiplicand 1011. Okay, and then you do the addition. So you do this addition: 1 1 plus 0 plus 0 1, 1 plus 0 plus 0 1, 0 plus 0 plus 1 1, 1 plus 0 plus 1 2 0, and 1 carry, 1 plus 0 plus 0 1, and then 1. Okay, so this is how you do it. Now this is, if you look at it, multiplication of multiple bit numbers, it is basically two operations together. So you have to find out the partial products. You can find the finding the partial products is very easy in binary. Okay, so either the multiplicand is there or it's not there. Okay, and how do you know that? So if the bit of multiplier that you want to multiply it with, if it is 1, then the multiplicand will appear, otherwise zeros will appear. And when you move from uh, the least significant bit to the most significant bit of the multiplier, so you shift the partial product by one bit position. Okay, so multiplication, binary multiplication of multi-bit numbers, it is basically binary shifting. Okay, binary shifting and then adding. So these are two operations that are used to implement binary multipliers. Okay, so shift plus add, these are the two operations that are used to uh, multiply two multi-bit numbers. Okay, this is the product. You can verify, okay, if it is correct or not. Now this is 1011, this is 11 in decimal, and this is 5. Okay, so the answer in decimal is 55. Now is it the same case? Let's see. So this is 32 plus 16, 32, and then plus 16, 48, 48 plus 4, 52, 54, 55. Okay, so this is 55 as well. You can verify. Okay, so we looked at all these operations: addition, subtraction, single bit addition, single bit subtraction, multi-bit addition, multi-bit subtraction, and then multiplication, single bit multiplication and multi-bit multiplication. Now we are looking at BCD arithmetic. BCD arithmetic, why do we need to study it? Now BCD is basically binary coded decimal. A BCD is a code. Okay, so we looked at it like in our last lecture. There was a slide where we talked about the difference between conversion and coding, and we looked at this example. I guess it was 13 or something. So when you convert 13 into binary, this is what you get. Okay, so when you convert 13 into binary, this is what you get. But when you code 13 as a BCD in BCD, this is what you get. Okay, so the 4-bit BCD code for 1 and the 4-bit BCD code for 3. So this is binary conversion and this is BCD code. Now why are we interested in BCD arithmetic? Okay, so BCD arithmetic, it basically, like, it is like working in decimal. It is like if you are adding two decimal numbers and you are getting the sum as a decimal number. ठीक है, so BCD is binary in decimal in binary. ठीक है, आप decimal numbers को ही ऐड कर रहे हैं लेकिन सिर्फ उनको लिखने का तरीका जो है वो बाइनरी के मुताबिक है. ठीक है, बाइनरी की तरह का है. तो how can you add BCD numbers? How can you add BCD numbers? Now if you remember our discussion on the BCD code, we said like BCD is used for coding decimal numbers in binary. Now how many decimal numbers do we have? We have 0, 1, 2, ठीक है, up until 9. So these are 10 digits. We have 10 decimal digits. अच्छा, 10 डेसिमल डिजिट्स को कोड करने के लिए हमने कहा कि जी हमें 4 बिट्स चाहिए. 3 से काम नहीं चलता क्योंकि 3 कैन रिप्रेजेंट मैक्सिमम 8 डिजिट्स. सो वी नीड 10 डिजिट्स, तो उसके लिए 4 चाहिए. बट 4 बिट्स जो हैं दे कैन रिप्रेजेंट अ मैक्सिमम 16 डिफरेंट सिंबल्स और क्वांटिटीज. तो इसका मतलब ये है कि BCD जो कोड है उसमें फिर हमारे पास 6 कोड्स जो हैं वो इनवैलिड कोड्स होंगे. दे विल नॉट रिप्रेजेंट एनी डिजिट. ठीक है, सो 6 कोड्स वुड बी इनवैलिड. मैंने शायद उस वक्त भी आपको कहा था कि ये 6 का नंबर आप याद रखें. ठीक है, ये 6 का जो नंबर है इसको आप याद रखें. ठीक है, वो यहाँ पे हमारे काम आएगा. सो 6 कोड्स आर इनवैलिड. ठीक है, हमारे पास जो कोड्स हैं वो 00 से स्टार्ट होते हैं. BCD जो कोड्स 8421 जो कोड है वो 00 से स्टार्ट होते हैं. इट रिप्रेजेंट्स द डेसिमल 0. और ये कोड्स फिर जाते हैं जी 1001 तक. दिस इज 9, डेसिमल 9. ठीक है, सो दीज आर वैलिड BCD कोड्स. उसके बाद वाले जो कोड्स हैं 1010 which represents a decimal 10, so this is invalid in BCD. ये BCD में invalid है. और उसके बाद तमाम कोड्स 1111 तक ये सारे invalid हैं. So they do not correspond to a BCD digit. They are invalid. ठीक है, और ये 6 invalid कोड्स हैं. ये कोड्स जो हैं वो 6 कोड्स हैं जो कि invalid हैं. अच्छा, जब आपने BCD में नंबर्स को ऐड करना हो तो इसका मतलब ये है कि आप डेसिमल नंबर्स को ऐड करेंगे और सम आपको फिर चाहिए इन बाइनरी कोडेड डेसिमल. यानी द सम शुड आल्सो बी अ डेसिमल नंबर बट कोडेड इन बाइनरी इन एन अप्रोप्रिएट कोड. ठीक है, उसकी एग्जांपल देख लें. से फॉर एग्जांपल दिस इज 8 एंड दिस इज 5. अगर ये इनकी बाइनरी रिप्रेजेंटेशन है. If you convert 8 into binary, this is how it would look. If you convert 5 into binary, this is how it would look. And all the decimal digits, their BCD code is basically their binary conversion. ठीक है, उनका binary conversion है लेकिन 4 bits में. अच्छा, BCD addition आप कैसे करेंगे? First you will carry out binary addition. जैसे normal आप binary addition करते हैं. Treat them as binary numbers and add them together. So इनको आप ऐड करें. जैसे 8 प्लस 5 इनका सम होगा 13. ठीक है, इनको आप ऐड करें. 0 प्लस 1 इज 1, 0 प्लस 0 इज 0, 0 प्लस 1 is 1, 1 plus 0 is 1. Okay, there is no carry, so it was easy. If you look at this number, this is 1101. ठीक है, it is 13. Now 13 is not a valid BCD code. It is invalid. ठीक है, ये वो invalid codes हैं. मैं आपको तमाम यहाँ पे चलें लिख लेता हूँ. So 13 is one of those invalid BCD codes 1101. ठीक है, अच्छा, तो अगर ये बाइनरी नंबर है और ये भी बाइनरी नंबर है और ये बाइनरी सम है तो फिर तो कोई मसला नहीं. there is no problem. But if we are treating it as a BCD digit and this one as a BCD digit, ठीक है, so then the sum is not in BCD format. ठीक है, सम जो है वो फिर BCD digit नहीं है. This is an invalid BCD code. Why? Because it is greater than 9. सम जब भी इनका 9 से बढ़ेगा तो 10, 11, 12, 13, 14, 15 इनके वैलिड BCD कोड्स 4 बिट्स में नहीं है. ठीक है, तो जो आपके पास जो बाइनरी ये कोड नंबर आएगा तो इट वुड बी इनवैलिड. ठीक है, तो फिर कैसे इनको करेक्ट किया जाए? तो मैंने आपसे कहा था ना ये 6 का नंबर आप याद रखें. So there are 6 invalid codes. So if you add 6 to this sum, तो आप वो invalid codes को फलांग जाएंगे. आप उन invalid कोड को उनसे जंप लगा लेंगे. ठीक है, तो यू वुड अवॉइड दोज इनवैलिड कोड्स। सो इसी प्रोसेस को यहाँ पे दोबारा देखें। सो दिस इज 8 एंड दिस इज 5, ठीक है, बाइनरी बीसीडी दोनों एक ही हैं। You calculated their sum, it turned out to be 1101, 13. 13 is greater than 9. This is not a valid BCD code for 13. 13 का जो BCD कोड है वो है 1 और 3 के BCD कोड्स यूँ कॉन्कैटिनेट करना। This is 13 in BCD, ठीक है, in binary code। तो कैसे आपको 13 मिलेगा? You just add 6 with it, ठीक है। अगर आपके पास sum of two BCD digits is greater than 9, you just add 6 with the sum, ठीक है। अच्छा, ये कैसे पता लगाएंगे कि वो ग्रेटर देन 9 है या नहीं, उसको हम बाद में देखेंगे। लेकिन आप इसको जब when you get the sum, when the sum of two BCD numbers, when you add them, it is greater than 9, so just चुपके से उसके साथ 6 ऐड कर लें। ऐड करें इसके साथ 6। so 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 2, which is 1 0, so 0 is the sum, 1 is the carry। 1 plus 1 plus 0, 2, which is 1 0, 0 is the sum, 1 is the carry, ठीक है। तो यहाँ से आपके पास there is a carry out, and then when you add these, 1 carry out यहाँ पे आपके पास इस एडिशन से आ रहा है, ठीक है। so if you look, आपके पास जो आंसर है वो ये होगा 1 and then 0 0 1 1। ये जो 1 कैरी आउट है इसको आपने इग्नोर नहीं करना, इसके साथ ये 3 zeros अपेंड कर देने। so this would be 0 0 0 1 and 0 0 1 1, ठीक है। So this is the BCD code for 1 and this is the BCD code for 3. So आपके पास जो sum आ रहा है, it is a valid BCD number, ठीक है। 8 जमा 5 और उसका sum आपके पास 13 आ रहा है और 13 is represented as a invalid BCD code, ठीक है। So in general, whenever you are adding two binary coded decimal numbers, तो अगर उनका डिजिट्स हैं, उनका सम जो है वो 9 से बढ़ के है, तो यू जस्ट ऐड 6 विद इट, तो वो करेक्ट हो जाए। करेक्ट है मुराद कि इट वुड बी अ करेक्ट बीसीडी नंबर, वो जो कोड होगा वो वैलिड होगा। ये बीसीडी हम क्यों कर रहे हैं? तो इनिशियली जो डिजिटल कैलकुलेटर्स और डिवाइसेस बने थे तो वो भी एडिशन वगैरह जो करते थे, तो इन ऑर्डर टू कीप थिंग्स सिंपल और डिस्प्लेज वगैरह को सिंपल करने के, डिस्प्लेज ऐसे होते थे कि मोस्टली वो बीसीडी नंबर्स को डायरेक्ट, यानी आपको उनको डेसिमल एक डिजिट उसका बीसीडी कोड देते तो वो उसको डायरेक्ट डिस्प्ले करते थे। सो इफ़ द सम वाज कैलकुलेटेड डायरेक्टली इन बीसीडी, तो उन सिस्टम्स के लिए वो ज़्यादा साजगार होता था, ठीक है। अच्छा, नाउ दिस वाज द एडिशन ऑफ टू सिंगल बीसीडी डिजिट्स, ठीक है। अब ये डेसिमल और उनको हमने ऐड किया और उनका सम जो है ना उसको हमने करेक्ट बीसीडी फॉर्मेट में लेके आए। Now if you have multiple BCD digits, फिर क्या करेंगे? So for example, we have these two decimal numbers 2905 1897 और हम इनको चाहते हैं कि BCD में ऐड करें, ठीक है। So this is 1897, this is 2905 and we are adding, these are BCD क्या कहते हैं नंबर्स, यानी डेसिमल नंबर्स हैं लेकिन उनको हमने बाइनरी में कोड किया हुआ है, एंड वी वांट टू ऐड देम इन बाइनरी एंड देन हैव द आंसर इन बीसीडी, यानी करेक्ट डेसिमल उस फॉर्म में लेना चाहते हैं। अच्छा, कैसे करेंगे? सो स्टार्ट विद नॉर्मल बाइनरी एडिशन। दिस इज 1 + 1 2, प्रीवियस कैरी 0 है। अच्छा, 2 मतलब 1 0, तो 0 हमारे पास सम हो गया, 1 कैरी। 1 + 1 2, 0 1 carry, 1 + 1 + 1 3, 1 is the sum, 1 carry, 1 + 0 + 0 1। अच्छा, now अगर आप इनको बाइनरी इनकी एडिशन करें तो दिस इज द सम यू गेट। इफ यू लुक एट इट, दिस इज एन इनवैलिड बीसीडी कोड, यानी इसकी बाइनरी वैल्यू 12 बनती है, 12। दिस इज एन इनवैलिड बीसीडी कोड, सो यू कैन नॉट, दिस कैन नॉट अपीयर इन द सम। तो क्या करें फिर? इसको करेक्ट करना है। कैसे करेक्ट करेंगे? हम इसके साथ 6 ऐड करेंगे। सो व्हाट इज 6? इट इज 0 1 1 0, ठीक है। अच्छा जी, सो ऐड देम। सो 0 + 0 इट इज 0, 0 + 1 इट इज 1, 1 + 1 2, 2 is 1 0, तो 0 यहाँ पे आया और 1 यहाँ पे आया, ठीक है। 1 plus 1 is 2. अच्छा जी, और प्लस 0 2 अगेन, तो 2 is 0 1 0, 0 यहाँ पे आया एंड 1 यहाँ पे कैरी हुआ, ठीक है। अच्छा, सो इज दिस फाइन? यस, इट इज परफेक्टली फाइन। कैसे? सो अगर आप देखें डेसिमल में दिस इज 7 और दिस इज 5 डेसिमल में, सो 7 जमा 5 12, ठीक है। सो 12 में 2 यहाँ आना चाहिए और एक कैरी होना चाहिए इनटू द नेक्स्ट डिजिट। यानी अगर हम इनको यूं ऐड कर रहे होते, यानी दिस इज 1 8 9 7 एंड दिस इज 2 9 0 5, अगर आप डेसिमल नंबर्स की तरह इनको ऐड करते तो क्या करते? 7 जमा 5 12, 2 1, 1 जमा 9 10, 0 1, 1 जमा 9 10 जमा 8 18, 8 1, 1 जमा 1 2, ठीक है, 2 जमा 2 4, so the answer would be 4802। अच्छा, वेरीफाई करेंगे कि whether we get 4802 or not। So let's come here now, let us add these two together। So 1 plus 1 plus 0, it is 2, 2 is 0 1, 1 plus 0 plus 0, it is 1, no carry out, 0 plus 0, it is 0, no carry out, 1 plus 0, it is 1, no carry out, ठीक है। So there we didn't have any carries here। Now look at this number, this is 1010, yeah, 10, 10 is an invalid like BCD, there is no code, BCD code for 10। So what should we do? We should correct it. How do we correct it? We add 6 to it, okay? So let's add 6 to it। Okay, so this is 0 plus 0 is 0, 1 plus 1 2, it is 0 1, 1 plus 0 plus 1 2, it is 0 and 1 here, 1 plus 1 plus 0 2, 0 and 1 carry out, okay। So 10 यानी 0 यहाँ आ गया और 1 यहाँ पे carry out हुआ, ठीक है। Okay, so this is also fine। Now let's add these two, this is 8, this is 9 and this is 1, ठीक है, 8 9 1 जैसे कि यहाँ पे था। Now let's add them। 1 plus 0 plus 1, ठीक है। So what is it? 2, 2 क्या है बाइनरी में? 1 0, so we have 0 1, 1 plus 0 plus 0, this is 1, 0 plus 0, this is 0 and 1 plus 1, what is it? 1 plus 1 is 2, 0 and 1 carry, ठीक है, 0 and 1 carry। अच्छा, 1 carry जो है यानी now like the sum is again greater than 9, ठीक है। This 1 carry, like we cannot ignore it, the sum is again greater than 9। In this case the sum of these two digits, like if you count this one here, uh, if you count here, so the sum here is 2 plus 16 18, so the sum is greater than 9। If the sum is greater than 9, we need to add 6 to it, ठीक है। तो उससे सिर्फ ये होगा कि ये जो पोर्शन है ये प्रॉपर जो सम है उसके साथ अलाइन कर जाएगा, ठीक है। सो वी नीड टू ऐड 6 टू इट। अच्छा, so add it, 0 plus 0 is 0, 1 plus 1 is 2, 0 1, 1 plus 0 plus 1, it is 2, 0 1, 1 plus 0 plus 0, it is 1, ठीक है। and this one, like, it already appeared here as a carry, तो carry हो गया था, but इस case में where here apparently the digit, it looks like a valid sum, ठीक है, but it is not valid, ठीक है, आपका जो BCD में जो result होगा, it will not be correct. Why? Because when you calculate the sum of two BCD digits, you have to look at the entire value of the sum, कि ये जो sum है, is it greater than or equal to 9? If it is greater than or equal to 9, do not like consider कि अच्छा ये 1 यहाँ पे चला गया तो ये जो बकाया 4 बिट्स हैं ये तो valid BCD कोड है, 2 का कोड है, नहीं. When you calculate the sum of two BCD digits, you have to look at this entire sum and see if it is greater than 9. If it is, you have to add 6 to it in order to get the correct BCD sum. And this one would, in any case, go here as a carry. Okay? Now, let's complete this sum. So 1 plus 1 plus 0, it is 2, which is 0, 1. 1 plus 0 plus 1, 2, which is 0, 1. 1 plus 0 plus 0 is 1 and 0 plus 0 is 1. Now here the sum is 4. Okay? So 4 sum hai, 4 has a valid BCD code. We don't need to add anything. So ye, it will appear as 0, 1, 0, 0. Okay? Now if you look at it, this is 4, this is 8, this is 0, and that is 2. Okay? So 4802, you have the valid BCD sum of these two BCD numbers. Okay? So this is how BCD addition works. Again, this is important. You should know it. Okay, how BCD numbers are added. Acha. Then our discussion of codes, like it is not complete codes का जो है ना सिर्फ ये नहीं है कि information representation. That is not the only purpose of codes. Codes, the purpose of code is also to detect error. Okay, when you are transmitting data, for example, when two devices are talking to each other or communicating with each other and they are transmitting data, so during transmission data can be corrupted. Okay, so a 1 can turn into a 0 or a 0 can turn into a 1. There can be single bit error, there can be multi-bit errors. So how do like codes handle such situations? So they basically use redundancy. Redundancy means that they add extra bits into the code word. So say for example, you want to send 10 different quantities or 8 different quantities, say for example. In order to send those quantities, you'll need a 3-bit code. Okay? But 3-bit code, the problem with 3-bit code in this situation would be कि if during transmission एक भी bit में error आ गया, so जो receiver है, the person will not know कि मेरे पास गलत data पहुंचा है या सही data पहुंचा है. ठीक है? So if you are using a 3-bit code to send 7 different quantities, so you have these combinations. ठीक है? 000, 001, 010, 011. ठीक है? Each is a valid code word. ठीक है? Each is a valid code word. अच्छा, किसी में भी error हो जाए ना, तो nobody would know कि invalid data send हुआ है या नहीं, because the receiver will always receive a valid code word. Okay? So say for example, this is a 3-bit code that you are using to transmit something. Okay? This can mean anything. These can be numbers, these can be the octal digits, or this can be anything. ठीक है? कोई 8 इशारे हैं, up, down, front, back, left, right, whatever. So these can mean anything. Say for example, you want to transmit this this particular combination, and this combination का मतलब है कि move forward. Say for example, and somehow during transmission ये जो 1 है ये corrupt हो जाता है and it becomes a 0. ठीक है? So the receiver, this is what you sent. It meant कि move forward, but the receiver received this thing because there was an error during transmission. And this is also a valid code. Yes, ऐसा नहीं है कि this is an invalid code. This is a valid code. And say for example, it means move backwards. ठीक है? Say for example, this is what it means. So receiver has received a valid code that says move backwards. You transmitted a valid code that said move forwards. During transmission, one bit got corrupted. ठीक है? तो what should we do? ठीक है? In this situation, you cannot do a lot unless कि दोनों आपस में मिलें कि जी तुम्हें क्या हो गया था, मैंने तुम्हें कहा कि आगे जाओ, तुम पीछे आ रहे हो। तो वो दूसरा बंदा कहेगा जी कैसे आपने मुझे ये कोड भिजवाया है, मैंने ये रिसीव किया है, और वो कह नहीं मैंने ट्रांसमिट ये किया है। ठीक है? So during transmission things can mess up. So how do you counter such situation? You can counter such situation by using redundancy. Redundancy से मुराद extra bits use करें. There should be invalid codes. There should be invalid codes. ठीक है? And you add another extra bit, say for example. ठीक है? So you add an extra bit. अब उसमें अगर एक bit खता हो जाए, so then you would know again उसकी अपनी limitations होंगी कौन सा bit corrupt हुआ है. So you would know, you would have the means to know कि ये जो data है this is wrong, ये जो command receive हुआ है this is an invalid code word. ठीक है? तो for example फिर आप transmit करते हैं कोई particular code और उसमें कोई मसला आता है. ठीक है? किसी bit में मसला आता है transmission में, so receiver would may receive an invalid code. May receive, there is a probability that the receiver may receive an invalid code. When the receiver would receive invalid code, it would not move backwards or forwards. It would request that the code be resent again, कि उस code को दोबारा से भिजवाएं. ठीक है? So this is what error detection and error correction codes are for. ठीक है? अच्छा, coding theory in itself it's a very extensive field. We are basically just introducing here simple एक code को बताने के लिए, that is called the parity code. ठीक है? वो parity, what do you mean by the parity code? तो parity code में क्या होता है? A simple form of redundancy is parity, यानी एक extra bit हम add कर देते हैं with the code word. ठीक है? What does that extra bit tell? That extra bit tells the parity of the code word. Parity से क्या मुराद है? Number of bits. ठीक है? अगर एक कोड वर्ड में नंबर ऑफ जो वंस हैं वो ऑड हैं तो it has odd parity. If the number of ones in a code is even, then the code has even parity. ठीक है? So odd parity और even parity से क्या मुराद है कि किसी भी कोड वर्ड में या किसी भी कोड वर्ड में अगर नंबर ऑफ वंस की तादाद ऑड है तो इसका मतलब है कि उसकी पैरिटी ऑड है, और किसी और कोड वर्ड में अगर नंबर ऑफ बिट्स की तादाद वंस है तो दैट इवन है, तो दैट मींस इट हैज़ इवन पैरिटी. अच्छा, बाज़ कोड्स होते हैं वो ऑड पैरिटी कोड होते हैं. उसका मतलब क्या है कि उनके तमाम जो कोड वर्ड्स होते हैं उनमें हमेशा नंबर ऑफ वंस की तादाद ऑड होगी. अगर कहीं ना कहीं वो इवन हो जाती है तो मतलब ये गलत है, इनवैलिड कोड है. ठीक है? बाज़ कोड्स होंगे जो कि इवन पैरिटी कोड्स होंगे. उनसे क्या मुराद है? उनसे मुराद ये है कि उसमें नंबर ऑफ वंस की तादाद हमेशा इवन होगी. अगर वो नंबर ऑफ वंस की तादाद ऑड हो जाती है तो फिर वो गलत है, वो कोड गलत है. तो अ कोड वर्ड कैन हैव इवन पैरिटी एज वेल एज ऑड पैरिटी. यूजुअली एक जो कोड होता है वो या सिर्फ इवन पैरिटी इस्तेमाल करता है या सिर्फ ऑड पैरिटी इस्तेमाल करता है. ऐसा नहीं होता कि वो इवन और ऑड दोनों को, फिर तो आप एरर डिटेक्ट ही नहीं कर सकेंगे. ठीक है? तो आइदर यू वुड बी यूजिंग इवन पैरिटी कोड, दैट वुड मीन कि उस कोड के हर कोड वर्ड में नंबर ऑफ वंस की तादाद इवन होगी, या आप ऑड पैरिटी कोड यूज करेंगे. उसका क्या मतलब है कि उस कोड के हर कोड वर्ड में नंबर ऑफ वंस की तादाद ऑड होगी. ठीक है? अच्छा, आई होप दिस हेल्प्स यू रिकॉल अ सर्टेन गेट जिसको हमने पढ़ा था, स्टडी किया था, the exclusive OR gate. ठीक है? So what is the exclusive OR gate? The exclusive OR gate is a gate which will give you uh, a 1 in the output when the number of ones in the input is even. ठीक है? And a 0 when the number of ones is odd. So exclusive OR gate and exclusive NOR gate, you remember those are important gates. ठीक है? तो वो यहाँ error detection के लिए you can use those gates. Now let's look at an example. This is an even parity code. ठीक है? An even parity code. This is an odd parity code. ठीक है? An even parity code, the number of ones would always be even. ठीक है? So what should be this bit in this particular code word ताकि इसमें number of ones जो हैं वो even रहे. So it should be 0. In order for it to be a valid code word, this should be 0. Why? तब यहाँ पे number of ones की तादाद even रहती है. अगर ये 1 हो जाए तो this would be an invalid code word in this even parity code. ठीक है, क्योंकि इसकी parity फिर odd हो जाएगी. What should be this particular bit? ठीक है, इसको हम parity bit भी कहते हैं. So this bit should be 1. क्यों? क्योंकि दिस इज़ एन इवन पैरिटी कोड और इसमें नंबर ऑफ वंस की तादाद हमेशा 1 रहती है, तो लिहाजा इसको 1 होना चाहिए ताकि वंस की तादाद 2 रहे, विच इज़ इवन. सॉरी, नंबर ऑफ वंस की तादाद हमेशा इवन रहती है. सो दिस बिट शुड बी 1 so that the number of ones stays 2 or even. Similarly, this bit should also be 1. Why? ताकि इस कोड वर्ड में भी नंबर ऑफ वंस की तादाद जो है वो इवन रहे. ठीक है. नाउ अगर आप इन कोड वर्ड्स को ट्रांसमिट करते हैं एंड देयर इज़ एन एरर, फर्ज के ये बिट गलत ट्रांसमिट हो जाता है, 1 ट्रांसमिट हो जाता है, सो यू वुड नो कि दिस इज़ एन इनवैलिड कोड वर्ड. वाई? बिकॉज नंबर ऑफ वंस की जो तादाद है वो ऑड हो गई है, सो दिस इज़ इनवैलिड. सो यू वुड रिक्वेस्ट कि जी आपने जो कोड वर्ड भिजवाया था वो ठीक नहीं मौसूल हुआ, काइंडली उसको दोबारा से रीसेंड करें. Similarly, look here, this is 0 1 1 0, so this bit should be 0. Why? Because we need to keep the number of ones even. So अगर इसको 1 कर दूं तो number of ones पे 3 हो जाएंगे, तो फिर ये odd हो जाएगा, तो गलत हो जाएगा. Similarly, this bit should be 1 so that we have the number of bits even. This bit should be 0 in order to keep the number of ones even. This bit should be 0 and this bit should be 1. ठीक है. So this is an even parity code. In this particular code, all the code words, this is a single code word, this is a single code word, this is a single code word, single code word. All the code words have even parity. That means that the number of ones in each code word is even. Acha, this is an odd parity code. यहाँ पे number of ones must be odd in each code word. So what should be this bit? This should be 1. What should be this bit? It should be 0. This one should also be 0. This one should be 1 ताकि number of ones की तादाद 3 हो जाए. This one should be 0. This one should be 1 ताकि number of ones की तादाद 3 हो जाए. This one should also be 1. This one should be 0. So this is odd parity code. Why? Because each code word has odd number of ones. किसी कोड वर्ड को सेंड करते हुए अगर आपसे गलती हो जाए ट्रांसमिशन में, से फॉर एग्जांपल आप ये वाला कोड भिजवाना चाह रहे थे और दिस बिट अराइव्ड एज 0, रिसीवर के पास ये 0 के तौर पे पहुंचा, तो नंबर ऑफ रिसीवर को पता है कि दिस इज़ एन ऑड पैरिटी कोड, यानी दोनों पहले एग्री कर जाते हैं कि हम ऑड पैरिटी कोड यूज़ करेंगे या इवन पैरिटी कोड यूज़ करेंगे. तो उसको पता है कि वी आर यूजिंग ऑड पैरिटी कोड एंड द नंबर ऑफ वंस शुड बी ऑड. ठीक है, ट्रांसमीटर ने ये इत्मीनान किया होगा. बट आई रिसीव्ड अ कोड विद इवन नंबर ऑफ वंस, सो रिसीवर इसको डिस्कार्ड कर देगा एंड इट वुड रिक्वेस्ट द सेंडर वंस अगेन कि दोबारा भिजवाएं. ठीक है. So this is basically an example of an error detecting code. इसमें आपको पता चल जाता है कि error कैसे डिटेक्ट करना है ट्रांसमिशन में. दिस इज़ इम्पॉर्टेंट. तमाम जो डिजिटल कम्युनिकेशन है, मोबाइल कम्युनिकेशन है, इंटरनेट पे आप कम्युनिकेशन करते हैं, ये सारी जो कम्युनिकेशन है इट डिपेंड्स अ लॉट ऑन रिलायबल कोड्स. ठीक है, तो कोडिंग थ्योरी इज़ अ वेरी इंपॉर्टेंट एस्पेक्ट ऑफ कम्युनिकेशन. ठीक है. अच्छा जी, सो आई होप यू अंडरस्टैंड. देयर इज़ लॉट्स ऑफ डिटेल इन द बुक अबाउट दैट. मैंने आपको सिंपल उसका बेसिक आइडिया इंट्रोड्यूस कर दिया. देन वी टॉक अबाउट अल्फा न्यूमेरिक कोड्स. So alphanumeric codes are codes that are used to represent both alphanumeric characters. ठीक है. So आप अपनी बुक में अगर जाए ना, 4th edition में, digital design 4th edition by Mano and Saletti, so there is table 1.7 in the book. It basically shows you all the ASCII codes, the character codes for all the ASCII characters. Now ASCII is an abbreviation for American Standard Code for Information Interchange, so it arose there, so that's why this is how it's named. So it is used to represent both. It is used to represent alphanumeric characters and other non-printing characters as well that are found on your keyboard. ठीक है. तो तमाम वो जो कैरेक्टर बेस्ड डेटा है जो कि रिप्रेजेंट होता है इन द फॉर्म ऑफ दीज कैरेक्टर्स, फॉर एग्जांपल दिस CODE 1.7, ठीक है. So these are all characters. Now how are these characters stored inside your computer? They are all stored most probably as ASCII characters, ठीक है. Most probably they are stored as ASCII characters. Now ASCII, original ASCII was a 7-bit code, so the extended ASCII it uses 8 bits, ठीक है. So it uses 8 bits to represent information. Now जो information ये represent करता है उसमें there are 94 graphic printing characters, 94 characters that are printable, and then there are non-printable characters, ठीक है. जैसे ये enter है, carriage return, this is basically your enter key, the up arrow, down arrow, backspace, delete, uh, space character, ठीक है. So these are all non-printing characters. Then there are some non-printing characters which are used for record marking. Record marking से मुराद, if you have a file that contains different types of data, so and you want to basically mark कि कहाँ से text data शुरू होता है कहाँ पे ख़त्म होता है, so you can use these characters STX and ETX. These are their names, start of text area and end of text area, and they have their own binary codes, ASCII codes, and वो codes सारे आपको इस table में मिल जाएंगे, ठीक है. Again, like we are not going to spend a lot of time on ASCII. You can read it. This is simply very easy. ASCII has some interesting properties, ठीक है. इसमें 0 is not represented as all zeros, 9 is not represented as the binary code for 9, ठीक है. In fact, 0 is represented as 30 hex. So what is 30 hex in binary? It is 0 0 1 1, and this is 0 0 0 0. So this is the 8-bit ASCII code for 3, sorry 0, ठीक है. And 9 is basically this thing, 0 0 1, and then 1 0 0 9. So this is 9, the ASCII character 9, ठीक है. This is the ASCII character 0. So when you type 0 on your keyboard, this is how it is stored inside your computer's memory. When you type a 9, this is how it is stored inside your computer memory, ठीक है. They have no correspondings to the binary code of 0 or 9. Okay, so how are uppercase and lowercase, like if you remember these things, it would benefit you in some way, but it's not mandatory. This is 4 1 hex, ठीक है. A, capital A is 4 1 hex. So what is the symbol for capital A? What is the binary, sorry, ASCII code for capital A? 4 1. So 4 1 is 0 1 0 0, and 1 is 0 0 1. This is capital A. Small a, it just differs from capital A in the 6th bit. So small a may the 6th bit is different. Okay, 0. This is the 8th bit, 7th bit. This is the 6th bit. Small a may just the 6th bit. You flip it and you get the code for small a. Okay. Acha. Small a is 6 1. So this is 6 1 hex. इसमें सिर्फ फ़र्क जो है ना कैपिटल लेटर और उसके कॉरेस्पॉन्डिंग स्मॉल लेटर में 6 बिट का होता है, और 6 बिट आप फ्लिप कर दें तो यू गेट द सेम. अच्छा, डिलीट इज ऑल बिट सेट. सो डिलीट इज बेसिकली 8 ones. दिस इज डिलीट. दिस इज आल्सो इंटरेस्टिंग, ठीक है. डिलीट, दिस इज हाउ डिलीट इज ऑल ones. del key, जो del key, when you press the del key, so the code that is sent to the computer is 8 ones or 255. क्यों? Why? Because it is carrier from the punch card पहले, like in the early days of computing, computers were programmed using punched cards, ठीक है. So जब आप punch card, उसमें क्या होता है, कार्ड होते थे गत्ते के और उसमें सुराख होते थे, punch होते थे, holes. So those holes would basically represent ones, and the absence of hole would represent a 0, ठीक है. So here power is down and my battery says that we don't have enough power. So I'll stop here, and once the power is up again, we'll resume and finish this lecture, and then I'll upload the videos. Okay. Until then, Allah Hafiz.